let me give a bit of motivation. So, yeah, okay. What we have seen is that basically where you have this assumption on your environment for the random walking random environment, what was happening was that, okay, your potential was globally decreasing, but there were some hills in the potential, and these hills were mainly responsible for slowing down the process. Okay? And okay, if you remember, we had an expression for E k tau k plus 1. And this thing really looked like something like exponential delta V, where this is the barrier in front that you have, well, okay, the barrier that you have around this point K. Okay, so for this reason, yes, you have something like that. Yes, okay. So now the idea is that, okay, this thing here, okay, I mean, I can replace it now, this thing by, okay, just to make sense of things. I minus 1 omega to I. Okay, these variables, okay, we have not shown it, and it's actually difficult to show it. But if you look at this as a random variable, okay, so let's call it ui. The probability that ui is larger than t, well, it's something that decays like t to the minus gamma. Okay, so this is actually complicated to show. And you need an assumption on rho to prove this. I will come back to that later. But yeah, okay. It's not unreasonable because what you can extract from what we have done so far, okay, with the expression you have for ui, is that okay. And if you take now this thing, okay. Well, it shouldn't have a very different behavior, okay, because the randomness of the walk, it basically multiplies things by a geometric random variable. Okay, you're just at the bottom of your pit. You try to overcome it, and if you fail, basically, most likely you're still down. So you will do another try independently. So you will have basically a geometric with a parameter which is exponential minus delta V. Okay. So okay, so now these increments of tau, they are not independent, but the correlations are not super strong, okay? Because basically, you know that your walk never go back more than log n steps, okay? So basically, when you go to the future, log n to the future, what you're seeing is basically independent of your passive. So yeah, perhaps a good way to understand what the behavior of, well, the evolution of tau k is, and well, as a matter of fact, this helps you then to know the evolution of x star n and then of xn, is to understand how IID, sums of IID random walk with this tail behavior behave. Okay, so this is what we are going to do today. Prove limit theorems. So I do not call them central limit theorems because some of them are not centered. For a variable with this kind of tail distribution. And for some reason, I will exclude the case gamma equal 1. Okay, from now on, I will use the exponent. I will use alpha instead of gamma because it's more common. So I will exclude the case alpha equal 1, but this is an exercise in the list I've given you. Okay, so limit theorem for some of IID random variables, okay, without second moment. Okay, and of course, the assumption I will have is much stronger than not having second moments. Okay, so what is our assumption? So we let alpha be between 1 and 2, and we take 1 away. Okay, because, yeah, gamma between 1 and 2 is also an interesting case, okay, because this is a case where we know that we don't have CLT, so. And we assume that x1 is a real valued random variable such that, okay, okay, and I will consider also p in 0, 1. Okay, and I will assume that px1 larger than t is equivalent when t goes to infinity to p t minus alpha. And I will assume that p x1 smaller than t minus p t minus alpha. Okay, so what I mean is that really the absolute value of x as a tail, which is like tail distribution, which is like t to the minus alpha, and you have an asymmetry, which is p. And here there is a small abuse of notation. If I write something, well, equivalent to 0 times t minus alpha, what I really mean is this is a little o of t minus alpha. Okay? Well, you don't like to write that things are equivalent to 0 anyway. So. Okay, so you have to read this assumption in a special way if p is equal to 1. Okay? Or p equals 0 symmetrically. Okay, and I think it's more standard to use parameter beta. So I will just say that beta is equal to 2p minus 1 is the, okay, it belongs to minus 1, 1, and it's the asymmetry of the variable, the asymptotic asymmetry of the variable. Okay, if it's equal to 1, then my variable is really asymptotically positive. If it's minus 1, it's asymptotically negative, and if it's 0, it's symmetric. Okay, so now theorem, let xn be a sequence of IID random variables which satisfies star and Sn equal to x1 plus xn, the partial sum, then the limit when n goes to infinity of Sn divided by n to the minus 1 over alpha. This is equal to the alpha beta. Okay, well, this is a non-trivial random variable. Okay, I'm going to say more about the alpha beta in a moment. For the moment, yeah, what I'm just saying is that your limiting distribution, well, it only depends on two parameters. The exponent alpha, which is, okay, and yeah, this theorem is false when alpha is equal to 1. And we will see the reason afterwards, but basically you need, okay, you have a theorem, but you need to change a bit this assumption. Basically, it turned out that to have convergence in the case alpha equal 1, you need to have p equal 1/2. Okay, you need the process to be symmetric in some way. Okay. So yes. So let's make a remark to kind of understand the theorem and why this theorem is very different from central limit theorem. So okay, let's look at the typical behavior of the maximum of xn. Okay, the running maximum. Not the running maximum of the sum, the running maximum of xn. Okay, and so let's look at the probability that x star n is, say, smaller than Tn. Okay, for some Tn smaller than, that goes to some sequence Tn that goes to infinity, and we will try to calibrate this to get a non-trivial limit here. Okay, let's put an absolute value here. Okay, so this is equal to, well, 1 minus the probability that x1 is larger than Tn to the n. Okay, just because these things are IID. So you want, and this thing, okay, it's equal to 1 minus Tn to the minus alpha 1 plus little o of 1 to the power n. And yeah, because Tn goes to infinity, okay, this thing goes to 0, so you know that, okay, you have equivalence of the logs here. Okay, so if you take Tn, which is equal to, say, s times n to the 1 over alpha, well, here you get exponential minus, okay, so the n is going to cancel. Okay, you have a minus here. The n is going to cancel, and you get s minus 1 over alpha. Okay, so what this means, okay, is that typically x star n, okay, it is of order n to the 1 over alpha. I mean, in fact, this thing, okay, is just, we have just proved the convergence in law of x star n. Okay, so if you combine these two things, okay, and here you have no minus here. This means that, well, typically, oh, okay, I missed an assumption. Okay, so if alpha is in 1, 2, okay, assume that E of x1 is equal to 0. Okay, I mean, you can see why the theorem would fail by the law of large number. Okay, like this thing is larger than n when alpha is smaller than 1, so you don't need, well, you don't have a mean, so you wouldn't know how to recenter anyway. When alpha is between 1 and 2, you need to recenter. Okay, and you know that after recentering, basically, the behavior of this, well, it's the same as the one of the largest jump. Okay, so if you look at this as a process, basically the final value is of the order of the largest increments. Okay, so if basically, if you want a scaling limit of the process, for instance, you would get jumps, okay, because you would see these increments, this instant. These large increments in the limit, they would produce jumps. Okay, so something very different that you have in the standard central limit here. Okay. So how do we prove such a result? The path is kind of straightforward. You want to use Liouville theorem, okay? Yeah, for this, perhaps I need to state you a stronger version of Liouville theorem, because okay, what we did when we okay. So let me state you the version, and then you will tell me if you need a proof. Okay, so. Theorem. And what's a theorem? Okay, so you have yn n larger than 1, which is a sequence of real valued random variables. And the theorem is the following. If the limit of, when n goes to infinity, of the expectation of I xi yn is equal to phi xi for all xi in R, and phi xi is continuous at 0, then A phi xi is the characteristic function of some random variable y, and B yn converge in distribution to 1. Okay, so I don't know, the simplest version of Liouville theorem is if this holds and if phi is the characteristic function of y, then this holds. Okay? Here, you don't need to know anything about phi. You just need to show that it's continuous at 0, and then it gives you automatically that it has to be. So I don't know. If you're interested, I can give you the proof of A. Okay. Yeah, so far, any question about? Okay. So yeah, let's go. Okay, so these things. Okay, so the proof, there are going to be 2 steps. So the first thing I want to show is that phi continuous at 0, it implies that yn is tight. Okay, the sequence of distributions of yn is tight. Okay, meaning that the probability that yn is larger than k, it goes to 0 when k goes to infinity uniformly in n. Okay, and well, the second thing is that if yn is tight, then yn converges along a subsequence. Okay, and when I mean converges along a subsequence, it's in distribution. Okay, so along this subsequence, you know that yn converges in distribution, and you apply basically the reciprocal of this to get that phi has to be the characteristic function of something. Okay? And then you apply, the easy version of Levy's theorems to get that your convergence holds along the whole sequence. Okay. Yeah, so this thing is, this thing is quite general. It's called Pirogov theorem. And it's valid a large generality, okay? Perhaps not arbitrary topological space, but not very far from that. But yeah, we are going to see a kind of really short and easy argument that shows you this in the real case. Okay, I mean, I will still need to assume that you know about some portmanteau results, okay, but I think this will not be a problem. Okay, so let's go with A. So I will introduce a function. I will call it psi n, which is the expectation of cos psi yn. Okay, just the real part of the characteristic function. Okay, so basically we know that the limit when n goes to infinity of e cos psi yn of psi n of psi is equal to psi xi, where this is continuous at 0. Okay? Just because this is the real part of phi. Okay, so for this reason, because of continuity at 0, okay, what we have is that if you take, well, the limit when n goes to infinity of 1 over delta integral from 0 to delta psi n psi d psi, well, this is equal to, okay, let me tell you what we are going to prove, okay? What we want to prove is that given epsilon larger than 0, there exists delta positive such that P of yn larger than 1 over delta is smaller than epsilon. Okay, perhaps for, okay, for all n. Okay, I'm going to prove it for all n large enough, but this is the same. You just have to change the value of delta if you want to prove it for all n. Okay, so for this, what I'm going to use really is this integral, okay, the average along 0, the interval 0 delta of phi n of psi. Okay? And, well, because phi n is bounded by 1, okay, I can use dominated convergence to say that this converges to 1 over delta, the integral of 0 to delta psi xi dxi. So in particular, what we get is that yeah, for n large enough, okay, we have that 1 over delta integral from 0 delta psi n or delta sufficiently small n sufficiently large, n larger than n0 of delta. This thing here is larger than 1 minus epsilon. Okay, I mean, I'm just first taking delta sufficiently small so that this is larger than 1 minus epsilon over 2. Okay, and then I take delta sufficiently large. Okay, and then if I want this for all n larger than 1, okay, I'm just taking delta smaller because I know that yeah, individually these things converge to 1 when psi goes to 0. So. Write it. Taking delta even smaller star holds for all n larger than 1. Okay, and now we are going to use this to prove this. Okay, and I guess there will be a constant here. It will be a constant times epsilon. But, I guess you won't mind. Okay, so yeah, what do we get from this? Well, if you look at this, okay, this is what you get from this is that 1 over delta times the expectation of 1 minus cos psi phi n d psi is smaller than epsilon. Okay, I'm taking 1 minus this, okay, and I'm just replacing that by the expectation and taking the 1 into the expectation. Okay, so what's good here is that I have something which is positive, and I know that it's small, so I know that it will be small most of the case. And now the good thing is that, well, I can put the integral inside use Fubini, and I can compute this explicitly. Okay, so this part is missing, so I have to organize my notes better. Okay, so I guess. Okay, so let's try to compute this integral. Well, the integral of 1 over delta, it gives me 1. Okay, so I have the expectation of 1 minus, and then I have this integral of cos, and I think this just gives me sine, okay, integral from 0 to delta, sine, okay. 1 over delta sine delta psi yes. So this integral of cos, I mean, this is just give me the cardinal sign. I think this is how it's called. The cardinal side of delta psi. This cardinal psi of delta. Okay, I'm sorry, this is not this. This is yn, and this is yn. And I know that this is smaller than epsilon. Okay. But now, this thing, okay, what you can say about this function is that, well, it's continuous. Okay. This is divided by delta. Okay, what's in there? Delta psi yn. Okay. Delta. Okay, yes. Yn. Okay, I'm using the fact that the integral from 0 to delta minus cos psi u, okay, it's equal to 1 over u cos delta u, sine delta u. Okay, this is good. Okay, so yeah, so this thing is really sine of delta yn. Okay, so you don't need to know too much about this function. This function here, well, it's equal to 1 at 0. It's continuous. It goes to 0 at infinity. And it's never equal to 1 outside of 0. Okay? So basically, it means that away from the interval -1, 1, okay, it's bounded away from 0. Okay, so what you have is that yn larger than 1 over delta. It implies that sine delta yn is smaller than 1 minus eta. Okay, so because of this expectation, okay, it is larger than eta. Okay, where eta is just some fixed number. Eta it's equal to max u larger than 1 of sine u. Okay, so I think this is just sine 1, but okay, so this is larger than eta p yn larger than 1 over delta. Okay, and then you get the result. So you get that this is smaller than epsilon over eta, which is what we want. Okay, so this proves the part A. Okay, and now the part B is, I will not detail it so much, but it's not super complicated. What do you do for part B? We want to show that f yn of t converge when n goes to infinity to ft, where ft is an accumulated distribution function. And okay, we want this for all t for which f is okay, at which f is continuous. Okay, and we want this along the subsequence. Okay, convergence in distribution for real variables, it's the same as convergence of the accumulated distribution function. Okay, and convergence of this, okay, if you don't care about the limit, it's not super complicated to obtain, okay? So would anyone have an idea? I mean, even without tightness, how do you get a subsequence such that this converges? Not for all t, but for most t. Okay, let's say for all rational t's. For 1t. Yes. So for 1t, you use Boltzmann-Weierstrass, okay, because you know this takes value in 0, 1. Okay, it's good practice to. This is just p of ym smaller than t. Okay, so for one thing, you have convergence, and then if you want convergence for countably many t's simultaneously, you can use diagonal extraction. Okay, so by diagonal extraction, we have that f yn of q converges to, okay, let me call this, I don't know, f bar of Q for all Q in Q along a subsequence. Okay, I mean, I just take an enumeration of Q. Okay, I find a subsequence so that Fyn of Q1 converges. Then I extract a subsequence from this so that F of Q2 converges. Then I have a sequence of sequences, and I take the diagonal sequence, which is eventually a subsequence of all of them, okay? Meaning that it's not a subsequence, but starting from some term, okay, it will be a subsequence. And this will give me the convergence. And here, F, okay, is just the set of limits. Okay, so because each of these things is increasing, okay, I know that F is non-decreasing. So so we call F the CAD lag extension of F bar. So what do I mean by this? Well, I want F to be CAD lag, so I just define F of t, okay, for t in R. F of t is just going to be, well, perhaps the soup of Q smaller than t. Oh, perhaps, yeah, the inf is better. Inf Q larger than t of F bar of Q. Okay, this defines me a function. Okay, so okay, I won't do it, but what you can show is that Fyn converges to Fyn of t converges to F of t, okay, for all t at which F is continuous. Okay. Yeah, basically, you just approximate t by rationals, and you use the fact that both functions are increasing. Okay. Okay, so we are almost done. Basically, the only thing that remains to prove is that, okay, F is a CAD lag function. We just need to show that it's a distribution function. So the important thing is that to show that F converges to 0 at minus infinity and to 1 at plus infinity. Okay, but this is an immediate consequence of tightness. Okay, so what you have is that, well, okay, just taking, you have that F 1 over delta is smaller than, is larger than 1 minus epsilon, and F minus 1 over delta is smaller than epsilon from the thing I just erased, okay? Yeah, and I think this diagonal extraction argument, this is called Elie-Bray's lemma. So if sometime you hear this, this is what it refers to. Okay. So yeah, so now we just have to prove that the characteristic function of our sums converge. Okay, and perhaps I should tell you what will be the limit. Okay, before we try to prove it. Any questions so far? Okay, so let me just rewrite this theorem. So the limit when n goes to infinity of exponential I psi n xn, okay, where psi n is equal to psi n minus 1 over alpha. Well, it's equal to exponential minus C alpha beta psi to the alpha. Okay, so you see something very similar to the central limit theorem, well, except that 2 is replaced by alpha. Where, okay, and now I have to give you the expression of C alpha beta. And I think C alpha beta is okay, the integral of sine sine okay, let me write with you. Sine u to the minus alpha du plus, and then I got, okay, no, it's, sorry, it's not really a constant. It depends on psi. Okay, but plus sine of psi, and then I get the integral, okay, then I get, okay, minus I sine of psi 2p minus 1, okay, so beta, and then I get the integral of okay, I'm not sure about the minus here. We will see that in the proof, but yeah, what you should get is here. I guess let's put a minus, and I see here what you get is cos u over u, and then minus 1 alpha in 1, 2 to the minus alpha du. Okay, so just a comment, just to check that these integrals make sense. So this is integrable when alpha is between 1 and 2, and you have a, okay, and this is integral over R plus. So this is integrable when alpha is between 1 and 2, and somehow this integral is defined as a limit when alpha is between 0 and 1. Okay, you just using this alternate series criterion. Okay, and yeah, for this thing, well, you see, you need the minus 1 to make things integrable at 0 here, when alpha is between 1 and 2. And when alpha is between 0 and 1, when it's the same. As this thing is really, well, okay. When alpha is between 1 and 2, this thing is integrable. when alpha is between 0 and 1, well, the integral is defined as a limit. Okay. Okay, and because obviously this thing is continuous at 0, this thing is the Laplace transform of some random variable. Yeah, and okay, perhaps the last comment. The value of these integrals are explicit, but I think okay, it's better to have these integrals than the explicit value. So the value, they are explicit, okay. Here somehow, I mean, this is a complex exponential. So this kind of looks like a gamma function. Okay, so, yeah, I think the ratio between these two things, okay, it's tangent alpha pi over 2. So this is, in general, the expression you find here is, well, a constant, and here you have everything in factor, and here you will have this factor here. Any question about the result? Okay, we will check whether there is a sign here or not. I should have checked better. I think I pulled one or two sheets out of my notes when I came this morning. Okay, so you look at this thing, I psi n Sn. This thing is equal to I psi n x1 to the power n. And I can rewrite this thing, well, okay, I will rewrite it in two different manners depending on what alpha is. So this is 1 minus the expectation of 1 minus exponential I psi n x1 to the power n if alpha belongs to 0, 1. And this is 1 minus I psi n x1 plus, it's a plus or a minus that I want? I guess it's a plus. Plus I psi n x1 to the power n for alpha in 1, 2. Okay, so here there is nothing to explain here. I'm just using the fact that by assumption, my variables are centered. So I can just, this is equal to 0, but this would be convenient. Okay, and now if I call this phi of psi, okay, what we just need to show is that the limit when n goes to infinity of n, well, okay, let me write it just n we just need to show this. Okay, and we will be done. Just because, I mean, in particular, this implies that this goes to 0, okay, and then you just put in the exponential. Okay. Okay, and I'm writing things this way, but of course, the way we are going to prove it when alpha is between 1 and 2 is you adding this term. Okay, but the statement is the same. Okay, so let's do it first for alpha in 1, 2. Because it's slightly easier because you don't have to worry about these non-well-defined integrals. Okay, and it's a bit technical, so perhaps it's better if I drink some coffee before. Okay, but is this clear what we are doing? Okay. Yeah, and the reason why I wanted to do, why I thought it was interesting to make this class today is that, I don't know, usually it's something you don't really see, and this kind of limit theorems, I mean, I don't know, many graduate students, including my past selves, think about it as something very mysterious, whereas, well, it's just as simple as the Gaussian central limit theorem in a way. Like, okay, so see you in 5 minutes. is for xi larger than 0. Okay, not that it's less simpler, but this is because, well, you know that when xi, well, the Fourier, well, the characteristic function at minus xi, it's the conjugate of the characteristic function at plus xi. And here you see that, well, if, well, this thing, okay, phi of minus, here you already hide that phi of minus xi is equal to the conjugate of phi xi. Okay, just because in front of the imaginary part you have this. Okay, so this is one thing. The other thing is I want to introduce some notations. So I want to introduce measures mu plus, mu minus, absolute value of mu, and delta mu. Okay, delta mu is a sign measure. The others, they are positive measures. So what is mu plus? Mu plus, okay, I will just define them by these probabilities. So this is just the probability that x1 is larger than t. Okay, so if you want, it's a distribution of x1, but okay. Okay, so these are okay. These are measures on R plus. Okay, so this is the distribution of xt, but it's restricted to R plus. So in particular, mu plus is not a probability. Okay, it has a mass which is strictly smaller than 1. Okay, okay, it can be 1 if x only takes positive values, but in general. Okay, mu minus t plus infinity. Well, okay, I think you guessed what it is. It's p of x1 smaller than minus t. Okay, so it's, if you want, mu minus is a distribution of minus x1 restricted to R plus. Okay, and I think the rest you can, okay, so I think this is actually the distribution of the absolute value of x. And okay, so the important thing is that mu t plus infinity, this thing is equivalent to t to the minus alpha, and delta mu t plus infinity, well, this is equivalent to beta t to the minus alpha. Okay, again, if beta is equal to 0, I just mean that this is little o of t to the minus alpha. Okay. So let's see. What we want to, okay, and yeah, and okay, mu is equal to mu plus, let's see. Okay, so, yeah, so what is this thing? Exponential I psi n minus, okay. 1 minus exponential I psi n minus I psi n xn. Well, this thing, I can rewrite it as the integral over R plus of, okay, so I just want to use real part and okay, yeah, no. Yeah, of xi, okay, x1, okay, xi n u minus I xi n u d mu plus plus integral or minus 1 minus exponential minus I psi n u plus I psi n u d mu minus. Okay, and yeah, somehow I'm not super happy with that expression. Because basically we don't have an asymptotic for this. We have an asymptotic for the tail of this. Okay, so well, how can we make this appear? Well, you can just use integration by part. Okay, so the important thing is that here this function is equal to 0 at 0. Okay, so let me write this. I'm going to use the fact that if mu is a finite measure, okay, let me write what I want, and then we will see the condition for which this happens. So this thing, it's equal to this. I can derive here, and here I should put mu t infinity. Okay, and basically, yeah, this is true when phi is okay, differentiable. Well, let's say phi is C1 and increasing, and mu is a positive measure. Okay, in that case, so phi equals 0. Phi increasing, phi 0 is equal to 0, and phi increasing, and mu positive. Okay, in that case, this is true, well, simply because both integrals make sense, and this is just Fubini, okay? This is just writing that phi u is the integral from 0 to t, 0 to u of phi prime t dt. Okay, this is just Fubini and then you integrate. So, then you can replace this, okay, just by phi prime integrable, okay, because then the function is the difference of two things that satisfies this. Okay, so here, yeah, so this thing makes sense as soon as this integral makes sense. And here we are going to apply it, and this thing will work. So we can rewrite this as, okay, let me do it in the case of mu plus. So, okay, when you derive, basically, yeah, you get I xi n here, and here you get I xi n, and here you get 0. So you get integral of minus. Okay, but minus is not really important because, no, minus is important, yes. You get minus I xi n, and then you get exponential I xi n u minus 1. Okay, so you get basically this. Okay, okay. This is on one side, and on the other side, you get the same thing, but you will get you don't get the minus, so you get minus I xi n 1 minus exponential I xi n t mu minus t plus infinity. Okay, and now I can rewrite this using my notations with mu plus and mu minus. So let's see what's the real part of this. Well, the real part, okay, so here I have minus I sine and times I. So I get xi n times the integral of sine xi n u. And I get the same thing here because I have a minus here. I get the same thing here. I should get the same thing here. Yeah, I have minus, minus, minus. So I have 3 minuses and an I square. So I get mu t plus infinity. And then I get plus psi. Okay, so now let's look at the imaginary part. So here I get I times 1 minus cos. Xi n u. And here I get minus I times, I get, okay. On the first one, I get I times cos, I times minus cos, 1 minus cos, and here I get 1 minus cos times minus. Okay, so I get this integral 1 minus cos delta mu t plus infinity. Okay, so now you get the answer whether there was a minus or not. Okay, basically there is a minus in front of the cos. So when you take 1 minus cos, you don't have a minus. Okay. Okay, and we are going to show that this thing converges. And here I forgot the I. Okay, so we have to show that when you multiply by n. Okay, so what do we need to show? Okay, we need to show that the limit when n goes to infinity of n psi n sine psi n u. Yes, this is there is dt here, there is dt here, there is a t here, there is a t here, and here is dt. Yeah. U plus t infinity is equal to the integral sine u to the alpha du, and the same thing. Delta mu t infinity is equal to beta integral 1 minus cos u to the alpha d. Okay, and if you have this, you've proved the theorem. Basically, okay, so I'm going to do this with a bit of details, but basically, if you replace this by its asymptotic, what you obtain is just exactly this, just by a change of variable. Okay, so what you need to show is that what you obtain, the extra term you obtain goes to 0. Okay, so I think the argument is exactly the same, so I will just need to prove the first thing. Okay. So yeah. So what we have is that this orange thing here, I will write it as n psi n integral n psi n t mu t minus alpha dt plus n psi n sinus psi n t mu t infinity minus t minus alpha dt. Okay, so now I can okay. Let's look at A. So if I look at A, I just take u is equal to psi n t. Yes, okay. I need here psi to the alpha in front. Because this is just the C alpha beta psi part. But, there was this in front. Okay, so yes. So I take u to be equal to psi n t. Okay, so what this gives me, A is equal to, okay, so this thing here is du, okay, so I get the integral of sine u. Then I get t, it's u over psi n, so I get n. And here I get psi n to the alpha u to the minus alpha du. Okay, and well, this is what we want. Okay, psi n to the alpha. Okay, recall that psi n it's psi n to the minus 1 over alpha. So psi n to the alpha Well, this thing is exactly going to cancel this. Okay, so this is what we want. All good. So what about the other term? Well, the other term, you can do the same change of variable, and you get, so B is, let me call it B. So B is just psi to the alpha times the integral of sine u minus alpha, and then you have, okay, minus u minus alpha, but this is not very. And here you have mu, okay, so, okay, here you have, sorry. Here you get something different, so you have u minus alpha here, and here you get psi n yeah, you get, okay. You get this n that was never cancelled, I guess. How is it exactly? Yes. Here you get psi alpha u minus alpha, and here you get psi n mu u over psi n plus infinity d. Okay, so now you want to use dominated convergence. Okay, so now when you look at this, okay, this thing is smaller than c u to the minus alpha. Okay, this is true asymptotically because this thing is asymptotically that. Okay, but now the important thing is that, yeah, for when this is small, okay, you are going to bound this by 1. I mean, this is smaller than, this is basically just saying that here you're just using the fact that mu t infinity is smaller than c t to the minus alpha. Okay, because of the asymptotic, I mean, here you just have to, you're just using something close to 0. And this is trivial because this is bounded by 1. Okay, so because of that, you can use a dominated conversion theorem. This converges almost surely to 0. So by dominated convergence, this converges to 0. Okay, and we've proved our result, and you can do exactly the same for the second part. Okay, so now perhaps you want to know how you do things when alpha is between 0 and 1. And here I should just underline what the necessary modifications are. How do you deal with basically with non-integrable functions? Okay, so any question about this proof? Okay, so now alpha is in 0, 1, and basically we are dealing with this, this. Okay, and yes, so I want to say that this thing is still true. Okay, because okay, these things are integrable, there is no problem. Here's the problem that when I do this, I kind of lose integrability. This thing is still true because okay, so what I'll be using here is basically okay the fact that phi is periodic. So if phi prime is periodic. So if phi prime is periodic, this thing makes sense, right? Because this is decreasing. So you can this alternate criterion, it still works. Okay, if okay, not maybe periodic, but if you have sine waves, okay, this works. Okay, because you're integrating over a period, and then you're integrating something smaller over here. So you're just summing things that are decreasing in absolute values. Okay, so what I have here is that okay, what is always true is this. Phi du. It's this 0 to n phi prime of u mu phi prime of t mu t plus infinity dt. Okay, this is true because this is just the derivative of this function. Okay, it's equal to 0 after. Okay, so now you take m to infinity on both sides and you have convergence on both sides. So you have no trouble here. Okay, so then comes the next step. And yes, the next step is just, I guess, this. Yes. And you get this. Okay, so why is this true? Okay, and again, I can make this in the case of 1. Okay, so well, this is somehow the same thing as before. So what I'm going to prove here is I'm going to prove that here, if I integrate between 0 and psi n m, okay, this converges to the integral from 0 to n. No. Psi n minus 1. Okay, so this works really as before, and now I just have to show that the remainder goes to 0 when m goes to infinity uniformly in n. I'll be done. Okay, so integral from psi n m to plus infinity. So I just need to show it basically separately for this for the power thing and for the mu thing. Okay. So Okay. So yeah, what's this thing? Psi. So I have n, psi n, psi n. Is this exactly what we have? Psi n, yeah, t. T to the alpha dt. Yeah, I think this is exactly what we want. Okay, so this thing, I mean, just by change of variable, okay, I mean, even if this thing is defined as a limit, you can basically change variable. So this thing is really the integral from n to infinity of psi alpha u alpha sin u divided by u to the alpha du. So this does not depend on n, and this converges. This does not depend on n, and this converges to 0 when m goes to infinity. So there is no problem. Okay, and now if you look at, well, the integral, okay, it's the same thing. Okay, this is xi minus 1. Mu t infinity dt. Well, okay, what you can do, okay, let's assume that okay, you can assume that m is a multiple of pi. Okay? And you can put minus 1 to the m here. You just want to show that things goes to 0. So, well, this thing here, well, it's smaller than this. Okay, just using your alternate series criterion. Okay, and then you're done. M plus pi, I guess. M plus pi. Okay, and you know already that this converges to what you want, so and that yeah. Well, you don't even need to do that. I mean, here you can just replace this by the asymptotic, replace this by 1, and okay, you get that this is smaller than 1. That probably, I guess, m to the minus alpha. Yeah, I think this is probably smaller than c times m to the minus alpha. Okay, and I think we have a complete proof. Okay, so let me see if what I plan to say. So now it's time for the deep comments. Yeah, so perhaps just a comment on the variable z alpha beta that you obtain in the limit. So any question on the proof? Okay, so we have defined the distribution z alpha beta, and what you can check, okay, it's really an immediate consequence of the fact that you have this power of psi to the alpha appearing in the Fourier transform is that so if Z1 alpha beta, Z n alpha beta are IID, okay, with distribution. Okay, then what you have is that the sum from I equal 1 to n of Z alpha beta, okay, so let's say J alpha beta J. Well, it's equal in distribution to n to the 1 over alpha Z alpha beta. Okay, so basically, you know, if you sum n standard Gaussians, okay, what you get is a Gaussian with variance n, so meaning you get square root of n times the standard Gaussian. Okay, here you get the same thing, except that this 1 over 2 it's replaced by 1 over alpha. Okay, so this is why these variables, they are called alpha stable. Well, these distributions are called alpha stable distribution. And you see that, okay, if you, okay, so Gaussian is the two-stable distribution. Okay, and basically this distribution alpha beta, okay, parameterized by two parameters. Okay, so for a fixed alpha, they are parameterized by one parameter beta, which is the asymmetry parameter. Yeah, they are the only distributions that satisfy this. So for alpha equal 2, you have a, basically you have a, well, a one parameter families of distribution because you have this scaling parameter. But if you take things modulo scaling, you have only one variable that satisfies thing. Okay, here you have an uncountable family of distributions that satisfies this, okay, because you can play with this parameter beta, which is the asymmetry parameter. Okay, and yeah, again, I mean, if you just want to satisfy this for n equal 2, okay, you just have these solutions. These are all the laws that satisfy this. Okay, so these are the alpha stable laws. Alpha stable laws, they are in general not super explicit, but there are some specific cases. So, okay, so alpha equal 1 is special. And what you get is the Cauchy distribution. Okay, which is, okay, so the density is 1 over pi, 1 over 1 plus u square. Okay, and so this is a bit strange. You've seen that for all alpha between 0 and 2, except 1, we have a two-parameter family. Well, here Cauchy, I mean, I still have this scaling parameter. But I don't have the asymmetry parameter. This is what makes alpha equal 1 special. And in fact, you still have a two-parameter set of distribution because here, okay, you can subtract something. You can basically add constant to Cauchy variable, and they remain stable. Okay, because constants are solution of this for alpha equal 1. Okay, so this is the reason why alpha equal 1, I mean, this is the reason why the proof has to be different when alpha is equal to 1, because yeah, you cannot get an asymmetric distribution. You cannot get an asymmetric characteristic function in the end. Okay, and I mean technically, okay, I'm not claiming that I understand it very well, but the reason you see this thing. If this is t to the minus 1, okay, if this is t to the minus, if alpha is equal to 1 here, this is never going to be integrable. Okay? I mean, if you have a 1 here, you will have a, yeah, you have a problem either at 0 or infinity. Okay, so, so yeah, this is something a bit peculiar. You know, like you have this this parameter that basically you have asymmetric distributions for all the range of alpha except in the middle where you have this string thing happening. Okay, as an exercise, you can prove this theorem. Okay, where the limit distributions are Cauchy. To prove that theorem, okay, you're going to assume that the initial variables are symmetric, okay, which is slightly more than just having p equal 1/2. Okay? Because even if this thing is something small times this thing could mess you around. Okay, and it turns out that this is not the optimal criterion, but the optimal criterion. I mean, okay. So here's a theorem we have proved is optimal. What we are going to prove in exercise is not optimal. You don't need symmetry, but the optimal condition is something difficult to state. Okay, so this is the first thing I wanted to say. Well, another thing is once you prove a central limit theorem, or a limit theorem, the second thing you may want to do is to prove a limit theorem for the process. Okay, so you want to define, I don't know, S and T, which is, well, okay. Well, you define ST, which is the piecewise linear extension of Sn. Okay, and no, okay, no, okay. Or St is equal to St. This is another valid option, and then you might say, okay, what does S and T over square root of n converges to? Okay, and well, you can find the limiting process here. So let me call it yt, t larger than 0. Okay, and okay, what are the characteristics of yt? Well, first you have that. Okay, yt it has independent increments. Okay, so this pretty much has to be. This is directly. You can see this directly from the. If you have a convergence like this, then this has to have independent increments, just because this thing has independent increments. Okay. The other thing is that the distribution of yt for a single t, well, it's t to the 1 over alpha times z alpha beta. Okay, and this pretty much comes from this. And proving convergence to such a process, I mean, to proving the convergence of finite dimensional distribution, if you just want to define this process as a collection of random variables, basically, I mean, it's just like Donsko's theorem. What's difficult to prove in Donsko's theorem is the continuity. Okay, it's tightness in the path space. If you just to prove a convergence of finite dimensional marginals, it's really little more than what we have done here. Okay? So now the question is, in which path of space do you want to prove things? And the thing is that this process has no chance of being continuous. Okay, because you know that this sum here is dominated by big jumps, okay, by big increments. And these increments, you will see them as instantaneous jump here. This is the reason why you don't need to bother to make ST continuous in the first place. Okay, so what you will have is, well, okay, so YT is a Cadillac process. So what this means is that, okay, you can construct this family of random variable in a probability space such that almost surely this is Cadillac, okay, and this is the version of the process you're considering. And the convergence holds in some topology. Okay, and there is something important you have to consider in the topology. It's basically that, yeah, this topology cannot be the uniform convergence topology. Because basically, you want to say that these two paths, you want to say that these two functions are close. Okay, so if two functions are close to each other and they jump close together, okay, I mean, my process is nothing nice like this, but you want these things to be close. So basically, you need to have a topology where if you jump close by, basically, so basically the topology says there exists a time change, two processes are epsilon close. If there exist two trajectories, two functions are epsilon close, if there exists a time change of one such that after this time change the two are close, and I want this time change to distort not more than a factor, okay, 1 plus epsilon or 1 minus epsilon. Okay, and I want a time change that doesn't distort very much, such that these things are close together. Okay, so this is called Skorokhod topology. There are several of them, and then proving this convergence is quite technical. Yeah, and I wanted. Okay, so. Yeah, no, it's n to the 1 over alpha. Yes. Okay, and there is another case which is special for which you can compute things. It's alpha is equal to 1/2. Okay, alpha is equal to 1/2. Okay, it's okay. I will just take alpha equal to 1/2 and beta equals 1. Okay, so beta, when alpha is smaller than 1, okay, so the case beta equal 1 is a bit special because, okay, this process here, it makes jump. But basically, the rate of jump up and the rate of jump down, they are basically p and 1 minus p. Okay, I mean, the set of jumps is dense. But somehow, even if the two sets of jumps are infinite, there is one which is more. So if beta is equal to 1, basically it means that this process only makes jump up. Okay, so when alpha is between 0 and 1, you only have jumps. So it means that the process is increasing. when alpha is between 1 and 2, somehow you would only make jumps up, but you have also an infinite drift that compensate for these jumps. Okay, so that between the jumps, basically, you go down at infinite speed, but somehow in a continuous manner. Okay, so, okay, and if you want to get the asymmetric thing, basically, you take a linear combination of independent copies of the fully asymmetric thing. This is how this. Okay. Yeah, and what's this special case? So, would anyone have a guess of a like an increasing process? Okay, an increasing. Okay, so a variable whose support is an R plus and that satisfies this, or like a process whose support is an R plus and that satisfies this. So here you have t to the power 2. So 1/2, 2 is the inverse of 1/2, and 1/2 is the exponent for the Brownian motion, so perhaps we can look at Brownian motion. Basically, what you can do is you look at B star t, which is the supremum when s smaller than t of Bs. Okay, so this is an increasing process. And then you take y, which is a generalized inverse of B star. Okay, so it's CAD-like just by definition of the generalized inverse, and it will satisfy the right scaling property because of this. And basically, because you have available formulas for the Brownian motion, you can write down explicitly the density of this when alpha is equal to 1/2. Okay, in all the other cases, basically, there is an expression for the density. It's just the one that you get when you inverse the Fourier transform. So not super easy to manipulate. Okay, but you can get, for instance, asymptotics. Okay, yeah. The tail of this at infinity is t to the minus alpha times p at plus infinity, and t to the minus alpha times 1 minus p at minus infinity. Okay, so this, yeah, so we will start to study directed polymers starting from Tuesday.